Welcome back to Rust Coding Challenges. Today, the interview question so famous it became a meme: invert a binary tree. The story goes that a developer who built a tool used by millions got turned down by a big tech company for not solving it on a whiteboard. So let's actually solve it in Rust in the handful of lines that matter and see why it's far friendlier than its reputation. So, what does inverting a tree even mean? You take the tree and flip it into its mirror image, left to right. At every single node, the left child and the right child trade places. And you do that everywhere, from the root all the way down to the leaves. That's the whole task. No clever math, no tricky edge cases, just swap the two children at every node. Here's the flip in a picture. On the left, the original root 4 with 2 on the left and 7 on the right. Under 2 sit 1 and 3. Under 7 sit 6 and 9. Inverting mirrors it. 4 stays at the top, but now 7 is on the left and 2 is on the right. And it cascades down. 2's children, 1 and 3, flip to 3 and 1. 7's children, 6 and 9, flip to 9 and 6. Read the bottom row left to right and it's reversed. That mirror is exactly what our code will produce. Let's build it in Rust. First, the shape. A tree node holds a value and 2 optional children left and right, each boxed onto the heap, and the tree is just an optional node. That option is how Rust says this branch might be empty, then 2 functions: empty for now, invert, which does the mirroring and level order, a helper to read the tree back so we can see the result. Down in main, we build a small sample tree and print it before and after. Now the 2 functions. Here's the whole algorithm, 4 lines. We look at the current spot. If it's empty, there's nothing to do, and we stop. That's our base case. Otherwise, the one line that does all the work, swap this node's left and right children. Rust's mem swap exchanges them in place, no clones, no copies. Then we recurse, invert the left subtree and invert the right, and that's it. Swap here, then let the recursion carry the exact same move to every node below. The mirror falls out on its own. This helper just lets us see the mirror. It reads the tree breadth first, level by level, using a queue. Start with the root, then repeatedly take the node at the front, record its value, and push its children onto the back of the queue, left child then right. When the queue is empty, we visited every node, top to bottom, left to right, so the list it returns is the tree read one level at a time, which is perfect for spotting the flip. Run it before inverting. Level order reads 4, 2, 7, 1, 3, 6, 9. Then we invert and read again 4, 7, 2, 9, 6, 3, 1. Look at each level. 7 and 2 have swapped, and on the bottom row 9, 6, 3, 1 is the exact reverse of 1, 3, 6, 9. The tree is mirrored top to bottom from 4 lines of code. So why the fearsome reputation? There isn't much of one, honestly. The trick is to see that a big tree-wide transformation is really just one tiny operation: swap 2 children, repeated at every node. You don't write the traversal by hand, recursion does it for you, and the empty branch base case stops it cleanly. You touch each node exactly once, so it's linear time. Once you see it as one swap, everywhere, it's 5 lines. Quick recap. Inverting a binary tree means swapping every node's 2 children. In Rust, memswap flips them in place, and 2 recursive calls carry that swap into the left and right subtrees. The base case, an empty branch, ends the recursion. 1 visit per node, linear time, a famous question that turns out to be 5 honest lines. If these breakdowns help you get comfortable with Rust and algorithms, a tip keeps them coming. The wallets are on screen, and there's a Ko-fi link below. Thank you. That's Invert a binary tree, the interview meme, solved in 5 real lines of Rust. Next episode, another classic, detecting a cycle in a linked list with Floyd's 2 pointers, the tortoise and the hare. Subscribe so you don't miss it. Tell me in the comments which problem to break down next, and I'll see you there.